Hey, Professor, can I get a quick question?
Yeah, sure.
So I was just wondering, when you're doing conversions like that and you have like 101 converting to centimeters, that's like three significant figures, right? So do you have to cut off that trailing 5, 4 to keep the significant figures in that situation?
That's a good question. Yes, yes, you do. In this situation, you would. So 101 inches is, so if we have this number of significant figures, this is you can consider this an exact number. So what happens is that you just take over whatever significant figures that you have in that first quantity. So this would actually, so 101 inches in this case. But let's say if I measure it within this precision, this would be uh, oh, actually, you would have to do, so let's say uh, it would work out in this problem, but not necessarily in every problem. Where's my, hold on, let me find my eraser. What did I do with that? It's right there. Yeah. So first you would have to convert 100, so let's say if we have it within 1 inch, right? First you would have to convert this into a percentage, right? So, because it's around 100, we know that this is around 1%, plus or minus 1%, right? Now, the way it works when you're multiplying two numbers with significant figures is that you multiply the errors together. So if I had two quantities, I'm not in this case, this number is precise, right? If we have two quantities and there's two different errors, we multiply the error together. So it would be, if there was another quantity, let's say we measure an area where it's just two lengths multiplied by each other, I would multiply the two uncertainties together, percent uncertainties, and that's my uncertainty for the area, right? And in this case, since this is an exact number, all you do is, this is, the error is infinitely small, so you just take this percentage as your error. So for your new quantity, the error for your new quantity, I'll just, would be 56 times 1%. I ran out of room, sorry. Times 1%, right? So we just moved the decimal place over 2 places. So in this case, our error, I'll just write this whole thing, would be plus or minus 2.6, right? And then we could round this off to something more precise. It's 2.6. That means if we round it off to the nearest number over here, right? And then we don't need to put a decimal place over there because we have that. So, and then we could even round this up another one, since we only care about this one digit over here. So even the uncertainty has a significant figure, so it's plus or minus 3, and that's how you do it. So when you multiply two quantities that are that have some kind of uncertainty, you multiply the percent uncertainty, and then if there's a power law, you just multiply that uncertainty by the number of powers. There's all these little tricks to it to calculate the uncertainty. You need this for like a lab class, but yes, you have a.
Got it.
I don't. Significant figures aren't terribly important. Usually, it's good to know. Obviously, it's important to know, but this is
Okay,
much
thank
more
you.
material we have to cover. So. Um, if you look in the lab manual, there is a page on it how error propagates in these quantities. And when you do an advanced lab class, this is where you learn how to treat these error propagations in different materials. So, but yeah. So it's important to know that how to do the significant figures. So you just find the percent uncertainty, and then you use that to set your new significant figure for whatever quantity that you multiply. Okay. Any other questions, guys? That was a good question. Thanks, Dan. Okay. So that's how you convert units. And we were doing this problem up here. So we were converting the units over here in seconds, right, into days. So we have 200 seconds. Then we know that there's 60 seconds in a minute. So 60 seconds per minute. Or I'm sorry, since we're converting it, we have to do, I just realized the mistake by looking at my units. You have to have minutes up here because we're going from seconds to minutes. So there's 1/60th of a minute in a second, right? So that's what we write. We're converted into a larger unit. Then, so this converts our stuff to minutes, right? The units cross out. Then we convert it to hours. There's 1/60th of an hour in a minute, right? And then we have 1/24th of a day in an hour. And if you notice, if somebody wants to do the calculation real quick, this is 3,600, and then times it by 24. I don't remember the number off the top of my head. If you want to write it in, that would be helpful. But if you look, if we follow the chain of the units, seconds cancel out over here, minutes cancel out over here, hours cancel out over here, and we're left with, thank you, just in the nick of time. No, divide. What's the decimal place? Thank you. And in SI, that would be 9 point in scientific notation, I mean, that would be 10 to the minus 5, right? Yep. And this is your answer, right? And this is given in days. And what we did over here, by following the units, if you notice, I corrected my mistake, right? I instantly saw that the units were off, right? And it's very easy to write down your units as you go along, and this is a very easy way to find any mistakes because the units are set. They have a certain, certain base units in it, and then you know whether it's correct or not almost instantly. And this is called dimensional analysis. So when you do a problem, you want to do dimensional analysis. So let's say if I'm calculating force, don't worry about the equation or anything like that. It's just for the example. So let's say if I have this, right? The units of force is newtons. Like I said before, it was kilograms, meters over seconds squared, right? Now, let's say if I have two quantities and I multiply these two quantities and I multiply them together, right? I'll have, this is mass, so I'll have kilograms, and then acceleration is meters per second squared. Don't worry about it, we'll explain this later. And as we can see, when we plug in the numbers, let's say if we have 1 kilogram and 1 unit of acceleration, we can see that this is the same units. And this is important when you're doing harder calculations. Oh, thanks, yes. This is why science is done as a community. It's a community effort. Nice, we have pi in there. And we can always remember it, right? This 2, eat in 2 pies, right? So anyway, we use this as a tool to see if our more complex measurements are correct or calculations are correct by following the dimensions through here. And it's important to do this. So do it in the beginning, even though it could be obvious that something is correct. It's a good habit to get into. Okay, let's finish this chapter today. Converting units, we did that. Oh, I should also let you guys know, I follow the book pretty closely. There's definitely more material that I say that in the lecture than in the book, so it's important to watch the lecture and everything, because I go into a lot more detail than the book does. But I follow the book quite closely. I think it's valuable as a guide. I think it helps out a student to learn the material, because there's set parameters in it and set philosophy. So I follow the book quite closely. Okay. One more problem. So let's say if we're given area, right? This is a common, very easy thing to get wrong, right? Let's say if I measure an area, if I measure the length of a square, I have a square over here. This is 10 centimeters, and this is 10 centimeters, right? The area of this is 10 times 10 centimeters, right? So this is 100 centimeters squared. What is this in meters? Anybody want to take a guess? So we got one meter squared. Anybody else take any guess? So let's see. Let's actually explicitly calculate it using conversion of units, right? We want to go to meters squared, right? So now the common mistake, yes. So the common mistake is just to use one conversion factor, 1 centimeter. So the common way to do it, I did this when I was younger too. It's not intuitive, right? It's not based on how you normally deal with everyday objects and mathematics in general, right? So you did this. So there's 100 centimeters. 100. So there's 1/100th of a meter in a centimeter, right? And you just multiply it by this, and you're left with meters. But if we look at dimensional analysis, what does this give you? Yeah, so this gives me meters times centimeters. So if you have some crazy unit like this, then that would work out, right? If you write the units like this, then it actually is 1, right? You know, I don't see any problems with writing it like this, but nobody ever does it, obviously, because it just doesn't make any sense to have it in lengths in 2 different units. But if we want to convert it fully to meters squared, we do the 2 conversion factors, right? This times 10 centimeters right? And then obviously the centimeters cancel out with each, oh, I wrote it backwards. No, I didn't write it backwards, that's right. Sorry. And these centimeters will cancel out, and then you're left with 0.01 meters squared, right? So this is the importance of dimensional analysis and writing things out explicitly, because sometimes your intuition can be off. It's definitely important to go by your intuition, and when you solve a problem, you definitely want to be like, there's something wrong here. I don't know what's wrong. And then you use your intuition to guide your logic. And then you prove that it's wrong a certain way. And this is how scientists normally think. They don't say the intuition out loud because they don't want to, you don't want to say something that's wrong, right? You want to be like, well, I think it's this way. Let me work this out before I announce it to the world, right? And let me work it out and make sure it's 100% accurate before I state it, right? So you always want to check your answers, you know, and use your intuition as a guide to solve it. You know, this number doesn't look right. This is too large or something like that. And you figure out why it is, or why your intuition is off in this case, right? Your intuition can be wrong sometimes. So it's important to write it out like this, and then you can instantly see where you went wrong, right? Or so it's very important to be deliberative in physics, to the point of it being painful. It ends up pain in the end. It's like practicing scales in music, right? It's, you know, going up and down the scale. It's annoying, but in the end, to play Beethoven, you have to do that. So it's a necessary thing. All right, I think we're done with the first chapter. So let's see. Let me see if there's anything else that we need to cover. Oh, okay, yes. One other thing. So you hear the term order of magnitude. Does anybody know what they mean by order of magnitude? This number is off by an order of magnitude. What does that mean? So in order of, yes, it's a power, exactly. It's a power of 10. So an order of magnitude is 10 times the amount. So when I say 2 orders of magnitude, it's off by 100 times, right? 3 orders, 1,000. The reason why we use this is we work in a base of 10, which means our number system repeats every 10 digits, right? We've got 10 digits in our fingers. This is where we get the number 10. We could easily have a system that works in a base of 7, and you know, where the number system repeats every base of 7. And actually, for computers, use base of 2, right? Because our computers work in zeros and ones, so you have a base of 2, right? Everything is based off of two numbers in that system, right? But we work in a system of 10. It comes from the number of fingers we have. Yes. Binary system. Yes, exactly. So there's other bases out there, but we work in the base of 10. That's why it's an order of magnitude. That's why 10 is an order of magnitude. And in physics, a lot of the times when we predict phenomena, if we get within an order of magnitude, we consider it pretty accurate, because we work at such different scale and issues. So like if we're off by an order of magnitude, if we're within our accuracy within an order of magnitude, that could be pretty successful in an experiment. So, all right, so we'll move on to chapter 2. Let's take a few minute break, and then I'll come back at 1:30, and then I'll continue with chapter 2. Okay. See you guys in a few. I'm gonna exit the room so that we can start a new video. All right.